In this video, we're going to extend your understanding of organic chemistry reactions and the mechanisms that organic chemists use to describe these reactions. Now that you know that organic chemistry mechanisms are described essentially using curved arrows or curly arrows, and that essentially there are really only three different things that are happening: bond to lone pair to bond, and bond to bond. We're going to extend and ask the central question: can the plethora of organic chemistry reactions be organized into simple categories? We ask this because, to a novice, they're going to seem like thousands of different sorts of transformations that can happen for organic chemistry reactions. The thing is, if we can organize these many chemical reactions into a few simple categories, it makes it easier to actually see what's going on and see the commonality between these different reactions. As you might imagine, the answer to this central question is indeed a resounding yes. So let's take a look. Here are three different possible categories to organize organic chemistry reactions. Now, there are other categories, but these are by far among the more common. So I will take a look at each one of these, show you the reaction, show you the mechanism, show you what you need to understand for the purpose of this course. And fortunately, the titles for these reactions are quite descriptive. Addition reactions, as you might imagine, involve creating new bonds. The way that this happens is essentially the carbon-carbon double bond is broken, and new bonds are made to other atoms. Elimination reactions involve eliminating something, a small molecule, sometimes water, sometimes a hydrogen halide, or something different. As such, an elimination reaction usually results in the formation of a double bond. So addition reactions break a double bond. Elimination reactions result in the formation of a double bond. And lastly, we have the substitution reactions. As you might imagine, this involves replacing one atom or a group of atoms in a molecule with a different group. Literally, it's a substitution. So let's start with the addition reactions. So in teaching model number 2 of the Chem activity number 10, we introduce the addition reaction. Again, we're looking to create new bonds by breaking a double bond. So in this example, you see, for instance, this cyclohexene, and we're going to be reacting with HBr. So essentially, new bonds are going to be made between the carbon that was making a double bond and a bromine, and the other carbon that was involved in the double bond and a hydrogen. So we're adding these atoms to the carbons that were making the double bond. In terms of the mechanism, so you can see that it starts off with the pi bond of our double bond making a new bond. So this would be bond to bond, and then we're breaking the bond between the hydrogen and the bromine. So that would be bond to lone pair. And then there's the attack of the bromide that gets released at the carbocation that ultimately forms. So this is an example of an addition reaction. Now, you're not responsible, for instance, for starting off with an original reactant and having to produce the mechanism from scratch. We want you to be able to recognize the mechanism, and then you'll see also that if I give you all of the reactants and products, that you're able to insert the appropriate curved arrow. So let's do a little bit of practice here. So you'll see next in your course pack something that looks like this. So I'd like you now to be thinking, okay, we're doing an addition reaction. Now, as I say, when you're being assessed in an assignment or a term test, I won't ask a question exactly like this. But because I want you to start to familiarize yourself with what's actually going on, I'm presenting it in this fashion. So we've got the double bond. We know that we're no longer going to have the double bond in the product. And effectively, we're going to be adding the H and we're going to be adding the Cl. So to be consistent with what I've written under the mechanism, I'm going to show here we'll be adding an H, and here we'll be adding the Cl. That's all that essentially is happening. We no longer have the carbon-carbon double bond. In terms of the mechanism, now this is something that I could ask you to do. So note that I'm essentially laying out everything. However, I would actually already make the final product, and I would be asking you, well, insert the curved arrows. So in terms of the mechanism, it starts off with the following way. We know that the pi bond is going to be broken, so the electrons in the pi bond will make a new bond to that hydrogen. So that's bond to bond. And then we've got bond to lone pair. And in a sense, if you can see what the ultimate product, or pardon me, in this case, the intermediate that we form, you can predict those curved arrows. And then next, we know that the chloride gets added. So then we've got lone pair to bond. This is an example of the addition reaction. Now in class, of course, we will be looking at many more examples. So again, overall, what I'd like you to be able to do is, given the overall reaction like this, I'd like you to be able to recognize it. I'd like you to be able to say, oh, this is an addition reaction. Or if I give you the overall set of reactants, intermediate, and product, I'd also like to ask you to be able to write in the curved arrows. Okay, so we've met the addition reaction. Now let's look at the elimination reaction. So again, elimination reaction involves removing something, generally a small molecule, although the small molecule may seem kind of hidden, and you'll see what I mean in a minute. As a result, usually a double bond will form. So in our example of the overall reaction, you can see that we've got a hydrogen and a bromine. Now the reaction involves reacting this with sodium hydroxide. Ultimately, the H and the Br will be removed. And in a way, you could say, well, HBr will form, except it's not exactly as straightforward as that. We have here a sodium bromide ionic compound, and here's the bromine or the bromide that gets lost or removed. And ultimately, we also form water, which you can think of as being, in a sense, a combination of H plus and OH negative. So what's the molecule that gets removed, in a sense? Well, it's this HBr, except it's in the form of sodium bromide and water. And so I've tried to highlight that there's the bromine and there's the hydrogen that gets removed. In terms of the mechanism, so you can see that this one occurs in a single step. We start off with lone pair to bond, and then bond to bond, and then bond to lone pair. Effectively, the H and the bromine get removed. But you can see here in this mechanism why it is that it's water that forms, and then we end up with the bromide anion. And so here's our sodium bromide ionic compound. Here's an example where we can write in the mechanism. Now, overall, you can see that what happens is H and Cl will be removed. Here they are here. The H will be associated with an oxygen that was originally part of a water molecule. Now we're forming the hydronium ion. And here is the chloride that gets removed. Remember that when these things get removed, this results in the formation of a double bond. So what does the mechanism look like? Now this is an elimination reaction, but in contrast to our first example, this one occurs in 2 steps. So I'm just going to go back for a minute. You can see in this case, we have an elimination, but it occurs in 1 single step. Now this next one is still an elimination, but it will occur in 2 steps. First of all, the chloride leaves. Next, we have a water molecule here with its lone pair of electrons making a bond, and we have a bond to bond. Carbon making a bond to hydrogen. Because the hydrogen is being removed, those electrons are now going to make a new pi bond. So again, the chloride leaves. That would have been bond to lone pair. And then we have the water molecule with its lone pair of electrons, the oxygen, making a bond, lone pair to bond. And then finally, we have bond to bond. And so I should, of course, write in this pi bond right there. Again, the idea is that if we want you to fill in the mechanistic arrows, we will give you all the original reactant, the intermediate, and the final product. And your job is just to write in the curved arrows. Finally, let's take a look at a substitution reaction. So substitution involves replacing one atom, or group of atoms, with another atom or a group of atoms. So take a look. Overall, we start with a chloride that's attached to a carbon. We have sodium hydroxide. So this is an ionic compound. So we have sodium ions, we have hydroxide ions. You can see ultimately it's the chlorine, which will become chloride, and it's being replaced by the hydroxide, or the OH. In terms of mechanism, in this case, it occurs in one single step. So you can see here we've got lone pair to bond, and then in terms of breaking the bond between the carbon and the chlorine, we have bond to lone pair. One single step. So let's take a look at another example of substitution reaction. Overall reaction, we're going to see that we're going to replace the chlorine with this group right here. The chlorine will be removed, and we will end up with OH, OH. And so in terms of this, in a sense, intermediate product, that oxygen will actually have a positive formal charge. Generally what happens next is one of those H's will be removed. But in terms of just looking at the overall reaction and with the idea of water is replacing the chlorine, this is where we would end up. Now in terms of the mechanism, once again, just like that previous elimination example, this one also occurs in two steps. Now I should mention that it's not up to you to decide whether or not a reaction will occur in one step or two steps, but rather you recognize the type of reaction and recognize, is it happening in one step or is it happening in two steps? So it's not that you need to predict which pathway, it's just that you need to recognize what's happening. Now you may be wondering, why is in some cases the reactions occurring in one step and in some cases two steps? That's really the subject of a second-year organic chemistry course, but we will be discussing this a little bit more and a little bit later in the course when we look at kinetics. So in terms of mechanism, we have bond to lone pair, the chloride leaves, and then we simply have lone pair to bond where the water attacks. Very simple substitution. And now I'm going to write in the final product. Again, if we wanted you to work with this, we would already write in the product. Just trying to give you some extra practice on how to view these things. So what we've done so far is we've looked at addition reactions, we've looked at elimination, we've looked at substitution. In class, we'll review all of this, address any questions you may have, and then do some practice. I hope you have found this video to be a good overview of the simple classification of different sorts of organic chemistry reactions.